Right. So as we said last week, we talked about three types of heat transfer. And yes, you remember, we mentioned that heat transfer by conduction, the conduction heat transfer, we said the formula for heat transfer by conduction, we said it's Q dot is equal to the thermal conductivity, K, multiplied by the area, which is normal, the surface area normal to the heat transfer direction. So Ka delta T, the difference in temperature, divided by delta X, which is the thickness of the surface. And also heat transfer by convection, we said the same process. So we call this conduction equation is Fourier law. The heat transfer by convection, we are following the Newton's law for cooling, which is Q dot is equal to the H, which is heat transfer coefficient. We said that this heat transfer coefficient depends on the type of fluid and the type of flow we have, multiplied by the same thing, A. Here, A is the surface heat transfer area, which is, again, it's normal to the heat transfer direction, multiplied by delta T, which is the difference between both sides of between the surface and the fluid. And the last one, heat transfer by radiation. We said that Q dot here is equal to the emissivity. We said emissivity depends on the color of the surface, multiplied by sigma here. Sigma is a constant, Stephen Boltzmann constant, multiplied by the area and multiplied by the difference in temperature. But here in radiation, just mean you need to remember this. In radiation, the delta T is raised to the power 4. So we said times T1 or 2T2 to the power 4 minus T1 to power 4. Okay, and we said that the temperature here must be in Kelvin. So when you substitute T in radiation, it must be in Kelvin. Otherwise, you'll get wrong answer. In the other types, like in convection or in conduction, delta T, if you use Kelvin or Celsius, doesn't matter because it's difference, only difference. There's no power here. But once we have power, then this will make difference. So you need to have Kelvin units. Okay. Any question here with this summary? Right. So then today we'll go into deep in the heat transfer by conduction. And we will have different, we'll go to different subtopics in heat transfer by conduction. We will study or we will understand, or we know what do we mean by study heat conduction in plane walls. And also we try to simulate the heat transfer by thermal resistance concept. Also, we will talk about multi-layer walls and heat transfer through other types of surfaces such as cylinders or spheres. So let's go back to the principle of heat transfer by conduction, which we did last week. And just to give you an idea here about, again, or to try to remember again, how does the heat transfer from one side to the other side takes place. So, for example, we have this wall, as you can see, and there are two sides of the wall, as you can see. This is, they'll say, we call this outer side, and the inner side is from the other way. So this is, let's say, inside, and this is outside. Okay, and as you can see, the outside temperature is 3 Celsius. Can you see here? So this is the outside temperature of the wall. And as you can see, the temperature of the wall is 3 Celsius. So if you take any point on the outside surface, we will measure the same temperature all around the wall. So 3 Celsius everywhere on the wall. And if we have this condition, if we have this type of distribution of temperature, which is equal distribution or similar distribution of the temperature, then we call this condition is steady heat conduction, because the temperature is constant anywhere on a certain side. As you can see also inside, we have 20 Celsius everywhere. So we have here steady condition or steady heat condition. Okay, so we have steady heat transfer by conduction because both sides, the temperature are fixed anywhere on the wall, and there is no change of this temperature with the time. Okay, so we call it steady state heat conduction, right? Now we have inside, as we said, inside and outside. And because there is difference between the inside and outside. Inside temperature is 20, outside temperature is 3. Therefore, there will be heat transfer. We said last time, the heat transfer takes place if there is difference in temperature. If there is no difference, there is no heat transfer at all. Okay, this is the principle of heat transfer. So now, as you can see here, because of this difference in temperature, we have this heat transfer. And also, as you can see, the Q dot, the direction of Q dot, which is direction of heat transfer, is normal to the surface. So this is the surface of the wall. You can see that the direction of the heat transfer is normal to the surface. Therefore, when you want to find the area of heat transfer, you refer to this area, which is the area of square or rectangle, whatever type of the wall we have. So you just need to know the height and width of the wall, and then you just multiply H times W, you get the area of heat transfer. Okay, right. So now, simply then, because of this, we can other definition here. As you can see, it is isothermal, and because the temperature we said is constant on both sides, and steady because it doesn't change with the time. The temperature of each side doesn't change with time, and it's one-dimensional. One-dimensional means we are only considering this way of heat transfer. We are not considering this way, for example, or this way of heat transfer. We are taking only the major part of the wall, which is, the one that we mentioned, the area, the biggest area. The other area is not important or negligible in some cases, or most of the cases. But if you want to have, let's say, more specific analysis, then of course you need to add any other small parts of heat transfer in the system. But in general, in our, let's say, current study, we don't consider other two or three dimensional heat transfer. It's only one dimensional, which is the heat transfer through the major or the biggest area in the system, right? Okay, so I'm just taking some time here because I need you to understand the principle properly, and then we'll move more quickly, or more like now faster. So then if we apply now here, apply the energy balance on this wall. The energy balance here, it means that the rate of heat transfer into the wall, so this is the Q into the wall, minus the heat transfer out of the wall, out, must equal to rate of change of the energy of the wall. So if the all energy coming in left the wall, then this part of the equation will be 0, correct? Because the Q in equal to Q out. And this is what actually what happened in a steady state condition. In a steady state condition, we are assuming that we are in a balance, complete balance, the system in complete balance, and there is no heat captured inside the wall. So there is no heat like capture here. Therefore, everything coming in will leave the wall. And therefore, this equation can be reduced to this equation, this equation can be reduced to this mathematical form. So Q in minus Q out is equal to rate of change, or dE of the wall divided by dt. So if there's any change during the time, and because of there is no change within the certain time, then this part we said we're going to be 0. Okay. Any question? Okay. Now back to the equation that we use, the Fourier equation. We can write the equation here, which is the one that we put last time, minus Ka dt by dx, and we said that dt is delta temperature, temperature 1 minus temperature 2, and dx, which is the thickness. Here we call it L, so dx means the thickness of the wall, and of course we said K is the thermal conductivity of the wall, and last time we mentioned that thermal conductivity depends on the material, right? So different materials have different value of K. Okay, we get K value from tables, or sometimes like they give it to you in the question. And if the rate of conduction, heat transfer, and the wall area are constant, of course, wall area will be constant, doesn't change, then we can end up with this equation, the last one here. This is the equation that we're going to use for every heat transfer by conduction. All right, we took it last time, the same thing, but this is the general equation of heat transfer by conduction. Okay, so any question before we move to more complicated cases? This is the general form. All right. Okay, now, as you can see here in these two figures, we have like a resistance here. If you look at this one here, R, we call it R. heat transfer, we are trying to make this analogy and simulate the heat transfer through any surface or from any surface by simulating the principle or the transfer by a resistance, electric resistance. So, and we give it simple R. So for example, here, if you take this one here, take this figure, this one represents a thermal resistance circuit. And as you can see, in thermal resistance circuit, we need to have difference in voltage, V1 and V2, in order to have current, I. So the current would not flow through the resistance without having difference in voltage, right? And because of this, we can simulate same thing in the same principle. We can simulate the heat transfer through the wall by same principle. We can say the temperature difference between T1 and T2, that is the reason that creates heat transfer, which is what we said before. Heat transfer cannot take place without having temperature difference. So now we have something similar to the voltage difference in the circuit. Rather than have saying voltage difference V1 and V2, now we have T1 and T2. Okay, and what's the term that equivalent to the current? Do you know what is flowing through the wall? Can someone tell me what's the thing that flowing through the wall, which is similar to the current in the circuit? Yes, Faisal?
So heat.
Yeah, exactly. So Q dot actually here is the flow in the wall. So heat is transferring through the wall, and while in the circuit was the current. So now we have difference in voltage. We substitute by difference in temperature, and the flow current of the current we substituted by Q dot, which is the heat transfer. So now we have something similar to the circuit. So the only thing that we didn't have is the resistance. So the resistance in the circuit basically is the difference in voltage divided by the current. We can do the same thing here in the heat transfer. We can say R is equal to difference in temperature divided by, rather than we say current, we say Q. Okay, so this is the resistance. All right, so we're gonna do this now. We apply this for every heat transfer by conduction case, and you will see, like later on, this will make the analysis of any system easier than using the just this equation and when we solve the problems, because sometimes we have very complicated systems. It's not only one let's say one surface. We have different surfaces, some of them in series, some of them in parallel. So unless we do the resistance design or resistance analysis, it's going to be like the process will be too long, or sometimes will be complicated without showing the resistance. We call this resistance thermal resistance. So here R is thermal resistance, while R in the circuit, electric circuit, we call it electric resistance. So we have difference here. RE, which is electric resistance. R here in heat transfer, we call it thermal resistance. So just remember this. Now, from now on, we'll call it thermal resistance. And when we talk about thermal resistance, just remember this figure. Okay. Right. So now we go back to the principle of heat transfer. We remember last time we mentioned this. We don't want to spend more time. So, but the thermal resistance will be applied in the three cases. So thermal resistance, for example, in convection, we said before, is this part. This is the thermal resistance, if you want to find it, which is the thickness divided by Ka. And how did you find this? Because remember, we said Q dot in conduction. We said Q dot in conduction is Ka dt by dx. And because we said thermal resistance is delta T, sorry, Q or the Q is difference in temperature divided by resistance. So we take this part and put it underneath here. And we call the whole denominator as R. So we call this R. So that's why here in this equation we said delta T by R, which is this part. R is delta X, which is L or thickness divided by Ka. Okay, so this is in regard to the heat transfer by conduction. And heat transfer by convection will do the same. We'll take all the constant, put it in the denominator, and we call this part as resistance. And this resistance, of course, is 1 over HA. So if you want to find resistance by convection, just simply 1 over HA, while by conduction is L divided by Ka. All right. And radiation will be the same thing. We will take the part that we consider it as constant, and then we just mention that R is 1 over H rod, and H rod must have this equation underneath. must be calculated by this equation. Okay. So just we'll take this later on, one by one. I just want you to focus now on the conduction because this is our topic in this week. So just focus now on this part, and just know that R for conduction is L divided by Ka. Okay. Now, the reason we said that we need the resistance analogy, because we said that in complicated system, it's easier for us to find heat transfer if we apply thermal resistance analogy. Okay, so for example, let's take the simple case. A wall has one layer. So this is the wall. For example, a wall from construct from brick, and the whole wall have one layer because only one layer of brick, and there is difference in temperature between in and out. So this is the inside temperature. This is the outside temperature. Because of this difference, we said there will be heat transfer. So we have heat transfer here. Q dot is equal to 10 watt. So there's 10 watt of heat transfer, 10 kilojoule per second. Oh, sorry, 10 joule per second. Okay. Now, if I want to analyze or want to simulate this heat transfer process by thermal resistance analogy, then I have 3 parts here, 3 heat transfer parts. First of all, heat will be transferred from T1, T infinity 1 to T1, right? So this is the heat coming to the wall, Q dot. And then because there is temperature difference between T1 and T2, this heat transfer will be continued so heat transfer will go through the wall, the same amount Q dot because of this difference until it reach the other side T2, and then from T2 to T infinity 2, there is another heat transfer. The same heat transfer will be the same amount of heat will be transferred from the surface to the surroundings, or maybe to the air surrounding the wall. So we have air, inside air and outside air. So first of all, heat transfer from the air to the surface. This is the first one, Q1, and then Q2 from the surface 1 to the outside surface, and then from outside surface Q3 to the air, outside air. So Q1 is equal to Q2, equal to Q2 equal to Q3. And of course, this is the equal to Q dot, the heat transfer. The total heat transfer is the same amount of heat flowing from air, inside air to the wall, and then from inside the wall to this outside wall, Q2, and then from outside wall to the outside air, Q3. This is the same amount of heat transferring through the wall, okay? So if I know any one of these, it is this heat transfer Q dot, which is the heat transfer through the wall, okay? And I can see here, I simulate the heat transfer between the air, inside air and the wall by R convection, because heat transfer in the air takes place by convection, not conduction, correct? And inside the wall, can you see here, this is thermal resistance 2, is through the wall. So this is by conduction. And the last one, thermal resistance 3, as you can see, from the wall to the outside air, again, it's by convection, not conduction, because as we said, heat transfer through the fluid will be by convection, mostly by convection, not conduction. So we have 3 resistances here, as you can see. We have 3 resistances. We have resistance 1, R1 by convection, R2 by conduction in the wall, and R3 by convection again from wall to outside air. And if I want to know the total resistance, what should I do? R total here. Can someone remember from electricity unit?
Plus together.
Sorry?
Plus them together.
Exactly. Thanks, Janshi. Thank you. Because they are in series, they are connected in series. As you know, if there is thermal resistances connected in series, then simply just add them together. So plus you get R total. So R total will be R1 plus R2 plus R3. Now, if I know the R total, I can simply find out Q dot, because remember before we said the Q dot is equal to thermal resistance, delta T, which is the difference in temperature divided by R. So now if I know R total, simply just put it here in this equation. I know the temperature, delta T, difference in temperature, then I can find out total heat transfer through the wall. Okay? Any question? Please ask if you don't understand. This is a very important principle here. Okay? Okay. Elias asking what lecture tutorial is the quiz going to cover? So don't worry too much about the quiz now, please. I sent you an email last week. So we'll talk about it at the end, please. Ask me at the end. Thank you. Okay, so let's go back to the slides. So now we know now what we mean by thermal resistances. And this is the case that we mentioned here. And already I mentioned this, that our total is the combination or the addition of the three thermal resistances in this wall. So we have convection, conduction, and convection. So for convection, we said 1 over HA. This is the thermal resistance by convection. So if I know H of the air, I can simply just say 1 divided by H divided by the area. So the area here is the same in conduction, convection, and the other side of the wall. The area is the same because we are talking about the normal area to the heat transfer. And we said that normal area is the area of the wall. So the three area here are the same. So the conduction is thermal resistance by conduction. We said it's L divided by Ka. And by the convection, again, same thing, 1 over HA. But this H here, out external heat transfer coefficient. Why is different here? Can someone tell me why H1? Both sides we have air, but why H1 is different from H2? Any idea? Just like, you know, you can mention any thing that you believe in. Why we have different H while we have the same fluid, we have same air, we have air inside and we have air outside. But what makes H has different value? Are they at the same temperature? The air inside and outside?
No, sir.
No, thank you, Abdulaziz. Because they are not at the same temperature, then the heat transfer coefficient will be not the same. And that's why we have different H. We have H1 and we have H2. And as I said before, these H values will be given in the question, or you will learn later on how to find H when we come to the topic heat transfer by convection. I will show you how to find H for each case. But at the time being, because we are not studying convection, we are studying only conduction in this lecture, we will give you the value of H. Okay, but just to let you know that we can find H by referring to the temperature, because temperature is different from in outside and inside. We can find H for each case. Okay, so we'll leave this later on. Okay, so this is the general equation of heat transfer, and we said that we can say Q dot is equal to delta T divided by R, as we mentioned before, or we say, or here R already given HA already included, the A included in R, or we can say Q dot is equal to U times A delta T, and UA, as you can see here, is equal to 1 over R. So it's up to you. It doesn't matter which way you take, but following the general form, this is the general form of thermal resistance equation. Okay. And remember, the units of R is given in this equation, Celsius per watt. So how many Celsius change per watt? Okay, So this is the thermal resistance unit. Right. Now we come to the more complicated case. Now in this case, we have only single wall, as you can see. In this case, as you can see, we have two walls. We have wall 1 and we have wall 2. And this is actually more practical case, because in most of the buildings, we don't have single layer of wall. We have multi-layers of wall. I will show you very soon different types of walls used in buildings. And because of this, it's not only one thermal resistance. We will have more than one thermal resistance in the wall. Depends on the material that we use or in the construction of the wall. Yep. So for this kind, let's say, of setting or design, as you can see, we have more than 3 thermal resistances. We have thermal resistance relates to this part of the wall between inside air and the surface of the wall 1. And then we have thermal resistance of this side, which is through the wall 1 by conduction. And then another thermal resistance by conduction again, but in wall 2. And the last one, thermal resistance from wall 2 surface to the outside air. Okay, so in this case, we have R1 here by convection, and then we have R2 by conduction, and then R3 by conduction also, and R4 by convection. Okay, these are 3 thermal resistances. Again, if you wanted to find total, our total, then our total will equal to R1 plus R2 plus R3 plus R4. You add them together to get the thermal resistances of total thermal resistance of this system or of this wall.
So
Okay.
excuse me, sir, is the
Yes, sir.
R1 is convection?
R1 convection, correct. Because between the inside air and the wall. Yeah.
Yes, sir, thank you.
And same thing, R4 also by convection, because we have also here air, but it's outside air. So R4 also by convection. R2 and R3 by conduction. Now, if I take each one of these, try to substitute the equation of thermal resistance, I can write the total thermal resistance equation. I'll show you very soon. So now if I take this is the, again, our total, it's our convection, which is between the inside air and the surface of wall 1, and our wall 1 by conduction, our wall 2 by conduction, and our convection 2, which is the last one, which is between the surface 2 of wall 2 to the ambient air or surrounding air. And if I substitute the value of each of these, convection has 1 over HA, and conduction, as you can see, the thickness of each wall divided by K1A. So each wall has different K, of course. Like if the construction of the wall consists of different materials, then K, of course, will be different. So we have K1 and K2. That's why you can see here L1, K1A, and L2, K2A. Yeah? Any question, guys? It's very important to ask now. Please ask now if you have any problem. Christopher, Imran,
All good, sir.
all good? Bakhtiar,
Sir, the H will be given, right?
Heat? No, actually, our target is to find the heat. So we have to need to find heat. Most of the questions, they ask you to find Q dot, because this is our aim. Our aim is to know how much heat we are losing or how much heat we are gaining from in the system. Okay, so this is what we need to find basically, right? But
So is H1 and H2 given?
yeah, the temperature most likely will be given because we know the temperature inside and outside.
Okay.
Because, for example, if you have a house and you want to design a heating system for the house, for example, you need to know how much heat you lose from the house. Yeah. So you say you take the worst case scenario in winter time. So say in winter time, the minimum temperature I have, for example, in Sydney, I have, let's say 4 Celsius nighttime. Okay, so I know that outside temperature is 4. This is outside temperature. And inside temperature, I needed to have a comfort, human comfort temperature. So most of the human comfort temperature is between 20 and 22. Okay, so now I know the temperature here. Inside, I know the temperature inside, I know temperature outside. Now it's your job to select what kind of wall you need to do. So if you know, let's say wall 1, you know K1 of the wall 1, for example, brick, you take it from tables, and let's say insulation K2. So you know these two Ks. Once you know these Ks, then, and you know, of course, the thickness of the wall, thickness 1 and thickness 2, this is your design. Then once you put all this information, then this equation can be solved easily. Correct?
Sir, which table?
I will show you the tables soon. But in heat transfer books or in any standard tables, there is K for each material. Okay, so you can find the K for each material. So I will show you these tables, but in case you don't have it, in standard books or in any heat transfer book, you can find the book, in the appendix, you'll have tables referring to the materials. So each material has its own K. Okay.
So one last question.
Yes, please.
You see A, is that the area?
Sorry, A?
Yeah.
A, yeah, the surface
Yeah,
area.
so does that mean it's like both walls or just one singular wall?
When you take it here in this equation, for example, for each wall, for each thermal resistance, you need to divide by the area.
Yeah,
But-
so the area is like both walls combined.
No, you just you missed maybe. This is the wall again. I'll draw it in 3 dimensions. So this is the wall. Okay. Is it clear for you? Who's Mervin, right? Mervin?
Yeah, I can see it.
So Mervin, can you see here? This is the heat transfer normal to the wall.
Yeah.
This is the area of the wall. And if you have, let's say, multi-layer of the wall. So this is K1. This is K2. But K1 and then K2 has same area because they are identical to each other, like they are in the same wall, correct? So the area of wall 1 is the same as wall 2. So the area,
Okay.
yeah. So you will use the same A in each term here. All these terms, you will have the same A.
All right.
You just need to find it once and then you divide by the A.
Yeah, okay. Thank you.
Okay. Right. So this is, I believe now, did I answer your question, right, Mervin? How to, this is the,
Yeah.
Okay. So, so now how do we know how to find the thermal resistance of more than one layer wall? Okay. Now we come just to this fact that in ideal design, we are assuming that if we have multi-walls like this, the one here, wall 1 and wall 2, this is ideal design. We are assuming that there are complete contact between wall 1 and wall 2, which means that if I, let's say, enlarge this, if I zoom in here, I take this part of the wall, there is a contact between both surfaces, complete contact. So which means that the smoothness of the surface is very fine, which makes the contact 100%. But in actual cases, the wall has roughness. If you like zoom in here, let's say, for example, this case, actual case of the wall, if you zoom in, this is what actually you see between two surfaces. Because of this, there are small gaps we can't see. You know, these gaps, let me put it in different color. You can see these gaps. These are the gaps I'm talking about. And these gaps filled with air because there is no 100% contact. So we have different heat transfer here. Okay, we will not take this case in our current study, but I just want to give you an idea. If you have an actual case and they ask you to find the thermal resistance of these contacts, then this is how we find it. So I'll show you, there are special tables here to find out the thermal resistance of contact, or we call it thermal contact resistance, because of these air gaps. And how to find RC, there are tables to find these ones, as you can see in these tables. So this is the table where you find the thermal resistance heat transfer coefficient. Okay, so at the time being, you don't need to worry too much about it, but just to give you an idea that we are working on ideal cases. Okay, actual cases, always the thermal resistance will be different between two surfaces because of this gaps, or these gaps between the surfaces. Okay, all right, so go back to our ideal case. We will have this question which give you a clear idea about multi-layer heat transfer, multi-layer surfaces heat transfer. But before I go there, probably it's better to show you, let me show you this slide, and then we go to this question back again. This slide, actually, I'll show you this slide. This will give you different types of wall, and maybe make it easier for you to understand why do we need multi-layer cases. So for example, this is a picture of a wall, a double wall, or actually three layers wall. So the first one here is the brick layer. This is a brick. Okay. And then we have another layer. We have a concrete block here. And then in between, if you can see it, there's a small gap. Can you see this gap? This is air gap. They put this as kind of insulation for the wall, because when you put air, you are increasing the thermal resistance of the wall. And this is actually what we want, to increase the thermal resistance of the wall so that we don't lose heat during winter time, and also in the meantime we don't get heat in summertime. So we keep the inside space at lower temperature during the year, okay, or like comfort zone, comfort temperature during the year. Okay, so this type of wall, as you can see. Another type, this is double brick, so with air gap between them. As you can see, we have layer 1 of the brick and layer 2, and also we have the air gap between them. Okay, and then this is another design here. We are using insulation. So we have brick outside, block, concrete block inside, and we have air gap, air here, plus the other layer here. Can you see this? This is insulation. All right. So we have 4 layers actually here. Okay. So when we want to find thermal resistance, how many thermal resistances we have in this, for example, in this case?
So 4.
Yes, thermal resistance by conduction, we have 4. And if we add thermal resistance by convection from both sides, then we have 6. Because the air inside and the air outside, then we add also another term from both sides by convection. So we have 2 by convection and 4 by conduction here. Okay. Also, this is another type of wall. This is a concrete wall. This is like a new design of concrete wall. They call it a pre-designed or pre-constructed wall. They do it in a workshop in a certain design, and then bring it to the site. Just install it, like assemble this in the site. So they don't need to mix concrete on the site. They just bring the wall ready and assemble this on the site. And this is actually one layer, but it has air gap inside. And this is like another type of the wall. Can you see many layers here? Because this wall actually using timber from outside, as you can see, and plasterboard or gyprock from inside. And as you can see, in between, we have so many layers of insulation. All these are insulation. Okay, so here we have timber. And here we have plasterboard. Okay, and then in between we have insulation. Again, for each case, we have to consider the K. All right, so the K, which is thermal conductivity, we must have it. We have different type of thermal conductivity because we have different layers of materials. We are not using the same materials, correct? So when you have different materials, we should use different K. The last one here, another design. This is actually another design of the wall. They call it brick veneer wall. So from outside brick and from inside plasterboard or gyprock. And most of the houses built here in Sydney is using this kind of design or this one. So they use either double brick or they use brick veneer. If you want to say make the construction light, the weight of the construction light, they do it brick veneer. It's easier, cheaper in building, and also lightweight. It has lightweight. Okay. Any question? Right. Okay, we go back to the question that we have here. This is the example of two multi or double glazed window. In double glazed window, this type of window used to reduce the heat loss from the building or heat gain by the building in summertime. And this is most likely used when we have a big glazed area in the building. If you see, let's say a building, all the building covered with windows, then definitely they should use or they have used double glazed window, because if you put the whole walls glazed, there is no brick, only, let's say, steel structure, and then you covered by you cover the gap by windows, then if you don't use double glaze, then you have a lot of heat loss and heat gain. And this means that you're gonna consume a lot of energy to heat the space inside the building or to cool it in summertime. And therefore, they use, you need to use the double glazed window. All right. So in this example, we're gonna use the Kahoot to solve it, but let's explain it to you now, and then we go to Kahoot and try to practice this more. So in this design, we have given the size of the window. So we have 2 meter height and 1.2 meter width. And we have the thickness of each layer of glass is 3 millimeter, as you can see. There is a gap, of course, between these two glasses, sheet or glass layers. And we have been given the K for each material. So we have given the K for the glass. And also we have given the K for air space. We have air in between, we said. So the air in between here, it has also K, because we need this K to find the thermal resistance of the air between the two glass sheets or glass layer. And as you see here, we are using K. It's air, we should use H, correct? Because we said in fluid, the heat transfer by convection is the highest or the most the highest value of heat transfer or takes place by convection. But in this case, we are using K or heat transfer by convection because the space is enclosed. The air is not moving. So that's why there is no movement of the air. It means there is no natural convection. And then the heat transfer by convection is small. The other type is conduction here. That's why we need conduction K, the K factor, because we need to find heat transfer by convection in the air space between the two layers. Okay. Also, we're given the temperature inside and the temperature outside. So we have inside temperature 24, and we have outside temperature -5. So it's winter time. Okay. Also, we're given, as you can see, we're given the H value for the air inside. As you can see, H1 is different from H2. Again, this is because of the temperature difference. So because of temperature change, we have change in H. So H1 is 10, H2 is 25. So all these values are given. Now, all you need to do here to remember how to find thermal resistance. So again, let's remember this again before we go to Kahoot. If I want to find our thermal resistance by conduction, so what's the thermal resistance by conduction? Again, we said we put L or delta X, the thickness, divided by K A. All right, remember this. So for each layer, the glass layer, the air layer, and the other glass layer, each one of them, we can use this R conduction. Now for the air in and air out, because the air here outside and inside, it's open and there is circulation of the air, then we have convection. So our convection here is equal to 1 over HA. Okay? 1 over HA. Right? Now, let me ask you a question here. What's our total? What's the equation of our total?
R1 plus R2 R3 plus R3 plus
Okay.
R4.
Okay, so let me do it this way. Just make it clear. So, oh, sorry. Oh,
So it's
yeah.
R
Okay.
convection plus R conduction plus R convection plus R conduction plus R convection.
Wonderful. Good. Faisal, right?
Yes, sir.
Yes, good, Faisal. Thank you. So our total here, as Faisal said, we have different thermal resistance. We have first one here. It's our convection for the air. And then after that, we have other resistance, our glass. The first layer of glass. And then we have thermal resistance of our air inside by conduction. And the fourth one here, our glass second layer. And you can see both layers are the same, correct? They have the same size, they have the same thickness, and the same material, glass. So basically our glass 1 is same as our glass 2. So if you find the first one, you can easily take it and use it in the second one. And the last one here is our convection. Outside, outside air. So this is in, this is outside. Okay, so this is will give us our convection in plus our glass 1 plus our air plus our G2 class 2 plus our convection out. So we have 1, 2, 3, 4, 5. So 5 thermal resistances. And each one of them, of course, you can say easily, this one is 1 over HA, H1, of course, and then this one, delta X divided by K A and so on. Okay, it's quite easy, really. Okay, do you have any question before we go to Kahoot?
So for the air inside the glasses,
Yeah,
so the formula will be same as delta X by K by A.
yeah, that's right. Because we said the air is enclosed and it's not open air, and therefore there is no circulation
So
inside.
the area will be calculated as same as the glass.
That's right, same as glass. So the area here, all the area are the same because we have the same surface area for all layers. So if you find the area at the first time, then it's the same for all other resistances because we are dealing with the same surface. We are not changing the surface. We are not changing here. We are not changing the surface area. It's the same surface area, but different layers, different materials. Yeah? Clear, Faisal?
Yes, sir. Thank you.
Any other question, guys, before we go to Kahoot? Please ask now if you, if you have any problem. Okay, let's go to Kahoot then. first take the attendance. Okay. All right, so let's go to Kahoot first, and then I will take attendance from there. Okay, guys, this is the number. Please enter the number. Okay, Elias. Elias. Can you hear me, Elias?
Yeah, I'm joining now.
Yeah. Muhammad, address. Muhammad, address. No, Muhammad does. Okay. Ahmad Bakhtiar.
Yes, sir. I'm here.
Abdulaziz.
Yes, sir. I'm here.
Faisal there.
Yes, sir.
Bandar is not there. William.
Yes, sir.
Jangshi.
Yes, sir.
Okay. Mervin.
Yeah, I'm here.
Maleh Tariq.
Yeah.
Imran.
Yes, sir, I'm there. Sir, I haven't missed any lecture or tutorial, but week 6, I can see that.
This one here, week 6.
Yeah, yeah.
Oh. I'll check the Kahoot. So you didn't miss any.
I was no, I don't miss any lecture or tutorial. I was in the Kahoot as well.
Okay, I'll check it then. Thank you. Probably this is the tutorial class. They use this sheet, this page before the.
I didn't miss any tutorial as well.
No, yeah, because I mean the teacher in the tutorial, I use this page rather than using the tutorial page. Yeah, no problem. Yeah, Muhammad Asif. Muhammad Asif. Neo.
Yes, sir, I'm here.
Thank you. Christopher.
Yes, I hear.
And the last is Peter.
Yes, sir, here.
Thank you. Okay. Right, so we'll go to Kahoot. Right, so everyone there, let's join then. So now you know the question that we been talking about. Let's start. So we have the area, so we have the dimension of the double glazed window, and you have thickness. What's the heat transfer area? It's very simple. Heat transfer area. Simply multiply W by H. Yeah. So we multiply this, you get the area. So the area, we said always the area normal to the heat transfer. So this is the window, and this is the heat transfer coming normal to the window. So I just need to multiply the width 1.2 times the height 2 meters. So these two, we can get the area of heat transfer. Right. Okay. What's the thermal resistance of this system? So this is the equation. The total thermal resistance, which one of these are correct? Remember how many thermal resistors we have and just check. We have one here, here. Yeah, good, perfect. Thank you. So it's, I think, quite easy, because we know that each one of these by convection from inside to the glass, and then inside the glass by conduction in through the air inside the glass, conduction, and then the glass, second sheet of the glass or second layer of the glass, also conduction, and the last one, which is to the outside air by convection. Yeah, correct. Okay. Now we have the H. What's the Rn? So if you know H, what's Rn? Remember R, we said for this convection is equal to 1 over HA. Correct. Actually, there is a trick here. Like you can see till here, this is the correct one, because also the unit is correct also. Can you see? All others have like no Celsius, but again, also the number is correct, of course. So that's what they need to find. So following this equation, this is how to find the value of heat transfer by convection. Oh, sorry, thermal resistance by convection. Yeah. Please ask if you don't get it. Ask, because we are trying to understand the principle that we already took. Okay. So now thermal resistance of a glass layer. Now we have R conduction, not convection, which is equal to correct? Good, everyone got it. And you know the trick now. You got this Celsius per watt. But of course, you need to find the value. But this is how to find the value following this equation. This is for conduction, thermal resistance for conduction. Okay. Right, so let's go to the final one. The last question. We have our total is given. What's the heat transfer? So now we know RT. So we know that Q is equal to delta T divided by RT. So RT for delta T is, you can see 24 and minus 5. This is the temperature in and out. So T out minus T in, or T in minus T out, divided by R total. Yeah. Okay, good. So anyone has a problem in finding this place, let ask now. If you have any problem in finding the Q or heat transfer by using the R total, the total thermal resistance, because this value already found from by adding 5 thermal resistances. Remember, we mentioned these thermal resistances. So we gave you the total now, but in the question, in the solved problem, you can find each one of them separately. But here, because we don't have time, we gave you the total thermal resistance. All you need to do is divide the delta T, which is 25 plus 5, because minus is 5, divided by 0.2539, and you get how much heat transfer through the wall. Okay. Right. So results here. These are number 3. Tariq number 2. Yangshu number 1. Thank you, everyone. Thanks for your participation. It's really helpful. I mean, you can find it later on that interacting with this class will make you progress very well, and also you answer like questions and do very well in the exam, final exam. Thank you, everyone. Right, so go back to the question here. As you can see, I will not go into details because we already talked a lot about it, but just to take it one by one here, first we need to find the area, and we said this area is the same for all layers because we have the same design. So the area of heat transfer is same for each layer, for the glass, for the air inside, and for also the external convection. So that's, we take them one by one. We find them one by one. We find the R1, which is the inside, and then we find R2 and R3. You can see here R2 and R3, all of them the same, which is equal to R glass. So we will do it once, and then it's the same for the other layer. So we have the glass here and the glass here. Both of them have the same R. And also we need to find the air inside. So the R of the air, which is following this again. For each one of them we have the thickness and we have the K. thermal conductivity. So just you need to divide it by the thermal conductivity and the area. You will get the R for each case. The last one, which is the outside, R for outside, same thing, it's convection, but we need to use different H. So as you can see, H here is different from H inside. Okay, but again, once you find these values of R, you just put them together, add them together, and you get the total R total, because they are connected in series. Again, we said before, in the circuit, if you have resistance connected in series, you just simply add them together. This is what we did actually, because these all resistances here are in series, as you can see. So all the 5 resistances are in series, so just need to add them together to find the total resistance. Okay. Let me see here. Okay. All right, so then to find the heat transfer, we can simply divide the difference in temperature between in and out, divide by the total thermal resistance, and you get the total heat transfer. Okay, any question, guys? I would say like this is very simple, but just need to practice this by yourself after the lecture. Try to do it yourself, please. You will get it. You'll know how to do it. All right. There is another requirement here. They want to know what's the temperature of the glass. You know that we know the temperature of the room, which is 24, sorry. But they need to know what's the glass here temperature. So it's also possible to know it because we know the R will take Q in this part, Q dot here, the first one, Q dot 1 is equal to, of course, Q dot total, because the same Q, it's series connection. So this is Q dot total. Then if I know Q dot, which is already given here, so I know the Q dot, right? And I say that Q dot here for this part is equal to delta T of this part divided by R convection. Correct? So I know T1 because already it's 24, it's inside the room. I know Q dot because already found it's 114. R convection is already given at the beginning here. This is R convection inside. If I use these values, the only unknown value is T surface, T1. So this is the only unknown. So I can find it. Sorry, we have this one, but we don't have this. So I can find T1 from this equation. And we can see that the glass temperature is lower than the room temperature, which is correct. Because the room inside 24, and as you go toward the outside temperature, we can find the temperature of each layer will be lower than the one previous or previous layer. So definitely you will find the temperature of glass 1 is higher than temperature of glass 2, because we are approaching, or we are going toward outside, and outside temperature is lower. It's -5, all right? So that's what we expect. Any question before we move to other topic? All right, so we still have half an hour. We can finish most of the topics in this lecture. So now we know how to find the heat transfer in flat surface or through flat surface. And we mentioned this, that the walls are a sample or example of actual surfaces we deal in our design or in actual design. So this is one application wall of buildings. Now, we mentioned these walls, as you see here. Some of the walls, as you can see, the layers stacked in parallel. So this is here, like for example, we have one layer here, wall, then after that there is another layer of air, and then other layer of wall or brick. So these are stacked in parallel. But in other cases, like say, for example, this wall, can you see this wall here? The timber plasterboard wall. We have, for example, first layer is timber, but then after that, that part of the wall, as you can see, these studs are timber studs. The heat transfer will also pass through these studs and also pass through the other part through insulation. So we have different materials at the same layer. And therefore, some of the thermal resistances here will be in series, while other in parallel. So we'll come to, I'll give you like more, I'll clarify this in the coming slides. So for example, here, in this setting here, we have heat transfer coming from this side. So heat coming from this side will go through the wall, but because of the different materials of each layer, we have in this part, we have first one, insulation. And then second one, we have material K1, and then we have K2, and then we have K3. And because of this different layer in each, different materials in each layer, we will have different Q. We have Q here, 1, Q.2, Q.3. Sorry, that is clearer. We have through insulation, Q.1, and then through material K1, we have Q.2, and we have material 2, we have Q.3, and then we have Q.4. And because we have different materials in this layer, it's no more one layer like before. It's not all of this brick or all of this insulation. It's stacked above each other. So Q total at the end, the total Q dot here total is not equal to Q1. It's actually the summation of all these Qs, Q.1 plus Q.2 plus Q.3 plus Q.4. Okay. So Q total you must add all these Qs to get the Q total. All right. Or the other way around is to find the R, the thermal resistance of the whole wall, and then you apply the thermal resistance rule, okay, which is easier, of course. So we'll show you how to do it, but just want to show you now, we'll tell you now, in each part, there is different heat transfer. No more similar heat transfer, like the one we took before, the case that we have walls stacked after each other. So each wall has the same material. Now we don't have same material, we have different materials. Okay, so we may have this in some designs. So I'll show you now for this kind of setting. As you can see, if I want to take, let's say, the Q, if I say this insulation means there is no heat transfer at all, so we just ignore these two parts now. We just take the inside Q1 and Q2. So Q total from these two is Q1 plus Q2. And if I apply the thermal resistance rule, as you can see, now these two thermal resistance, they are not in parallel, they are in series. So we have resistance 1 and resistance 2 in parallel. So I connect them to get the heat transfer. So this is the I coming from this side, which is Q, in this case Q. So if I take Q here, Q coming this way, Q total, and then divide it into two parts. One of them going to R1 and the other one to R2. Okay, and then we'll get the same Q at the end. So I need to know R1 and R2. I need to add them together. Now in parallel circuit, what's the R total? Do you remember the equation for R total and R in circuit? So in circuit design, we can say 1 over R total is equal to 1 over R1 plus 1 over R2. This is how to find R total in parallel connection of thermal resistance, same as in the circuit, electric circuit. In the electric circuit, if we have parallel connection, the total resistance is equal to 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. So you keep adding these terms until you get the total R total. Okay, so it's not similar to the to the previous cases when we have resistance in series. In that one case, we said this is R1, this is R2, and we said R total is just simply add them together. Say this plus this. Now, this is different case. We don't have this case now. We have this case, which is in parallel. Okay, and we apply this rule. Okay, so now, is there any question before I move? Right, so as you can see, the Q heat transfer is equal again, the same thing, same principle, delta T divided by R total. But here R total, we should refer to the parallel case. Okay, so this is the R total based on the parallel connection. And then once I found the R total, I can also, of course, can find Q dot. Any question, guys, before I move on? Please ask now.
So what does it mean by parallel layers is n? Is that like just around like another number?
Sorry, I say it again. I didn't get your question.
You says parallel layers is n. That's if it's like a bigger number, right?
Where do you find this parallel?
N.
Per layer. Yeah. That's right. Because if let's say here in this case we said we have only two. We have layer 1, R1, and R2, because we have 2 layers. But if I let's say have more than these two, n number of layers.
You just keep adding it.
Keep adding, right? Correct. Right. So let's say if this is 1, and then after that other layer, and then other layer, and then other layer. So you take the R of each layer, R1, R2, R3, and so on, R4. So when you add them together, he said R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Okay. So you get R total from this equation, and then you substitute this value in this to find,
Alright.
to get the Q total.
Yeah.
Okay. Thank you. Right. So any other question? If there's no question, then we'll move to the other case. So this is the case where we have parallel. Now with more complicated case, we have parallel and series. All right, same thing we do. We take the first part here. These two resistance are in parallel, so put them this way. We put it in the diagram here, R1 plus R2 in parallel. And then these two in parallel are connected to R3 in series. So these two connected to R3 in series, which is what we show here in the diagram. Okay, so first of all, you need to find the R total for the first one here, which is here R1 over R1 plus 1 over R2. So this is the combination of these two resistance. I must add them in series with R3 because R3 connect to them in series. To get, this will give me the thermal resistance, total thermal resistance. Of course, after I put this the parallel one, I should take the R total for that one and then add it to R3. But this is the equation, so I should maybe do it another way. Sorry. So this is equal to 1 over R, 1 and 2. Okay. So I find R1 and 2 and I can say that this one added to R3. So I'll say R1 and 2 in parallel plus R3. Okay, this will give me R total. All right. Okay, so we'll do this now again. We'll have the same principle. If I want to find heat transfer through this wall, then first I need to find the total thermal resistance and total thermal resistance following this equation. As you can see here, the first one, R1 to 2, is the parallel section. So this is the parallel section resistance. I add to it R3, and if I want to continue to the outer surface, then I have to add R convection to the air, outside air. Okay, so that's actually possible also. If there is inside air, outside air, then I will do the same thing. I put R convection inside plus R convection outside, and then add the other R of the material of the wall. Any question? All right, so this is something, getting harder now, but this is this question will simplify everything. Okay, this question has the combination of different thermal resistances. So this is a wall construction, and you find that this wall consists of many layers. We have brick layer. This is the brick. Okay, and to put or to lay out the brick in the wall, we need what they call plaster or filling cement. So the cement layer, as you can see in the surrounding the brick. Okay, so we already given the wall dimension, we have the height of the wall 3 meters, and the wall width is 5 meters, and it consists of brick size given 16 times 22 centimeter each brick, so we know the size of the brick. And the brick, of course, separated by, as we said, plaster layer or cement layer. And the cement layer thickness is already given. And also the K of each material of the brick and also of the cement already given. There are also 2 centimeter, sorry, this is the first one, sorry, the layer of the cement is between, we have like here, we have 3 centimeter, and also we have layer of cement in front of the brick, as you can see here, 2 centimeter. So all these dimensions are given now. We know these dimensions, the thickness of each plaster layer, the inner and outside temperature already given. So we have 20 inside, we have 20 inside, and we have outside temperature, which is -10. So -10 outside, inside 20. Also given heat transfer coefficient of outside air and inside air. So all these information are given actually. You can start finding the thermal resistance of each layer. The first thing you need to do, you need to find how many thermal resistances and the arrangement of these thermal resistances so that you don't do mistake. So let me clear this now, clear the comments. Now, as you can see, if I have heat transfer coming from inside to outside, because inside temperature is higher than outside temperature. So the Q here, the total Q, will be affected by many layers. May I ask you a question? How many, what do you think? How many thermal resistances we have, including inside air and outside air? Just think about it. Look at the figure here, and please try to find out how many layers of thermal resistances we have for this design. Take your time, like for 30 seconds, and I will ask you. Okay. Any clue? Ilyas, William, Tarek, Abdulaziz. Any clue? Jingshi, yes?
8.
8. Okay, so let's put this first one. This is 8. So this is 1. One of your colleagues said 8. Okay, Jingshi, 8. What else?
6.
6. So we have 6. 6 from Faisal. All right. Okay, 6. So William said 6. Bakhtiar said 6. Okay, let me check now. Let us check together. So we said the air, inside air, and we have outside air. Now we start taking this by convection, correct? This is 1, R1. And then as you see, going through the wall, the first layer of the wall, this is the foam. We have foam covering the wall. So this is R2. And then when we reach this section, can you see this section here? When I reach this section, I have 3 layers. This one, and this one, and also the brick layer. So they are in parallel, correct? So I have 2 layers of cement. In between, there's a brick. So I can divide this into 3 layers. Sorry, before I go there, this thickness of cement is another R. It's R3. And then I divide this to 3, 1. All these 3 layers of brick setting. After that, I have another layer of cement outside. And then the last one, which is the air outside. So if I say R1, R2, R3, R4, 5, R6, R7, and R8, perfect. Yes. Zhengxi, thank you. Correct. So this is the number of thermal resistances we have between in and out. Okay. Is it clear for everyone? Please ask. Faisal,
Yes, sir.
are you talking to me or because I can see your
No.
no? Okay. Right. So Abdulaziz,
Yes, sir.
clear?
Yeah,
Clear?
all good, all good. All good.
Okay. All right. So then let's go back then to the slide and clarify this details. So this is the thermal resistance circuit as we put before. And as you can see, the different layers. So the layer 1, layer 2, and then we have 3 layers here parallel to each other. And then this is the other one. And the last one is the external air. Okay, so all these were considered. Now, I take them one by one. I find R for each one of them and then add them together. Because as you can see here, these 3 are in parallel and in series, and these 2 are in series, connected to 3 in parallel. So first of all, you add the parallel ones together using the parallel equation, and then add this 3 circuits, 3 thermal resistance to the other thermal resistance in series. Okay, then so we found R1 convection 1. We have H given, the area, we know the area. We find the R1 of the foam, the pink color layer, this layer. All right. And then we find the plaster side, the cement side, which is both sides here, this one and this one. These 2 have the same thickness, correct? So if you find one of them, it will be the same as the second one. So R2 is equal to R6, as you can see. So we find it once. So they have the same thickness and the same material. So you don't need to repeat this one, sorry, 6, 2. You have the same K, same area, the same thickness. So they have the same value. Okay, so this is for the 3 layers Now you can find the parallel one, which is, we'll find out very soon. The parallel one, which is R2 and R6. Also, we said the plaster, that one we already found, but the R3, 5, and the plaster center, we're already given all this information. All right, so we have the parallel one. We can find these ones. We said this is part, and this one, and this one. And once we get this, they are the same R3 and R5. We just said R3 basically they are the same. So I put a different color. This is these two parts have the same thickness. So they have the same R, because same thickness and same material, they have the same R. And the last one, which is the brick, we know the size of the brick also. And that's also the convection of the air outside. So all these values can be found from the given information. Then now our duty is to find out the total thermal resistance. And as we mentioned before, we can add first the parallel resistances, these ones, to find their thermal resistance. And we can get this from this equation. And then after that, we can find it. This is the combination of the thermal resistances of the three layers in parallel. And then we add this to the other in series and other thermal resistances. As you can see, we have put this in the equation with the other in series, and we get the total thermal resistance. Now, if you know the total, now the solution becomes very easy, because I know the total, I know the delta T between in and out, divide the delta T by this value, you can get Q dot. So Q dot is delta T divided by R total. This is the heat transfer. This heat transfer, actually, we did it for the part of the wall. Remember, the wall size is 5, length and height 3. So we need to now to convert this to bigger size. Now we took this per this area, per 25 square meter area. All right. So we use this now, and this area to transfer it to bigger area. So if you know the ratio, they take the ratio of this calculation. So the ratio here, we know the ratio, we know the area of the wall, the actual area of the wall. We multiply it by this ratio of how much watt per square meter. We did this already by dividing the amount of heat by 0.25 meter. That section, we took it from the wall, and then we can find the total heat through the wall, which is 263 watt. Okay. So up to here, actually, up to this stage here, this is what you need to do. This is the important part of the question. because this is when you find the total heat transfer, the total, thermal resistance, and find out the heat transfer through a section of the wall. And after that, the solution become easier because you just need to do the ratio of this section to the bigger section of the wall, because the wall actually identical. I'll draw it again here. For example, if this is the wall, if I take part of the wall here, this side of the wall, and I find the heat transfer through this part only, I can take this and make it in a larger scale to cover the whole width and height. Okay, so this is actually what we did. We took only this part of the wall, and we found how much layers in this part, and then we converted this to a bigger size to cover the whole wall. Okay? Is it clear for everyone? Any question? This type of question, we had it in one of our final exam, maybe 2 years ago or 3 years ago. Yeah, you need to really understand the principle. If you know it, then it's quite easy. As I told you, it's open book exam, so you don't need to remember the equations, but you need to understand how to apply it. Which one is for convection, which one for convection? This is the major question here. Okay, right. So up to this level, up to this stage, we were talking about flat surfaces only. Heat transfer through flat surface. And we took different cases of different layers, different setting of the walls, different materials. Now, not all the cases flat surface. Sometimes we have to deal with circle surfaces. So in circle surfaces, such as this drawing here, this is where we have different setting of the wall. It's no more flat, it's circle. But do you know where we use this kind of surfaces? Like, where is the application of heat transfer having this type of walls, for example? Can anyone did anyone has an idea, or yeah, Bakhtiar? You want to talk, Bakhtiar? Bakhtiar, no? Nia?
No, sir. Maybe engines.
Well, correct. Engines, like some part of the engine, it's circle. Like in you know, the radiator in the car, there is a part we call it radiator, where we have water, cooling water
But they're
going
fins.
inside.
They're not really
Yeah.
tubes.
Yeah, exactly. It has so many tubes, and the heat transfer will be through the tubes. And because, of course, tubes are circle shape, then the heat transfer will be through circle surfaces. Yeah. So this is like one of the application. So in heat exchangers, you're going to have a heat exchanger experiment very soon, and also you're going to use this type of heat transfer, right? So in conduction, circle cylinder, we will have the same idea. Probably we will finish this next week, because I believe we still have so many things to talk about. So many slides here. So we'll but just to give you a quick idea that in circle setting, we have the same thing. We'll apply the same rule, which is the Fourier law of heat transfer by conduction. And this is the major law that we use every time. Remember this. But before, we used to have, rather than have dr, we have dx, remember? Thickness. Here, the thickness, actually the thickness of the wall. So rather than saying dx, we have dr. So this is the wall thickness. And because the radius between R1 and R2 are different, so we have R1 and R2. And because of this, there is change in R. So but rather than say delta X, we say dr, change in the radius of the tube, okay? And that's why we are using now dr here in the equation, not dx. And now if we do integration for the change in radius and change in temperature, the integration limit is for R1 and R2, the first side, left side, and the right side is for change in temperature. If we simplify this integration, we do the integration and simplify it, we can end up with the general equation of heat transfer in circular tubes or in circular design. And this is actually, again, we use the same general equation of heat transfer, but in this case, the R total must follow the circle setting or circle design requirement. So in circle design, we know that from integration that the R of conduction should be ln R2 by R1 divided by 2 pi Lk. L is the length of the tube, and K is thermal conductivity. And now the surface area of heat transfer, or the heat transfer area, is actually the surface area of the tube. This is the area of heat transfer. So the area of the cylinder. Okay, so the R total here is again the combination of R convection, R conduction, and R convection. So there is R convection inside of the tube, and then R conduction through the tube material, and then R convection to the fluid outside the tube. So we have 3 resistances, 2 convection and 1 conduction. And we should follow this equation to find R for each section or each convection, each heat transfer or each thermal resistance. All right. So we have 3 thermal resistance. The first one convection, second one conduction through the cylinder, third one convection to the surrounding fluid. Okay. Any question? All right. So I will stop up to here, because this is the first topic in cylinder or heat transfer in a circular cylinder. Then we'll continue next week when we have multi-layer of cylinders, same as we did when multi-layer of walls. We have multi-layer of cylinders in a system. So up to this, any question before we leave, guys? Tomorrow, as we said in tutorial class, you will have the quiz, and the quiz I sent you an email. It will cover the first law of thermodynamics and second law of thermodynamics. Basically, the question that we focused on. So we focused on the question before. Remember the question that we mentioned before? We have examples solved on turbine and examples solved on other systems. Try to understand these examples and also try to prepare your steam tables, because you're going to use steam tables in the quiz. Any question?
Sir, which tutorial?
Tomorrow class.
I mean, which tutorial is covering for the quiz?
Up to last week tutorial. And
It was
last
six.
week, last week lecture.
Oh, lecture. Okay.
Yeah, so last week lecture, we solved an example. And also before that, in week 6, we have other example on first law, and just try to solve these examples by yourself and understand how to use the steam tables. Because entropy also need to be found from these tables, the entropy.
Sir,
Yes.
do we need to submit our work or just?
No, it's also online quiz, like the first one.
Okay, thank you so much.
Okay, it's multiple choice. All right, guys. Any question before we leave?
Thank you so much. Have a good day, sir.
Thank you, sir. Have a good day.
Thank you.
Yeah, bye, sir.
Bye. See you soon.